Sometimes mathematics is seen as living in an ivory tower, speaking its own language and leaving the world behind in ever subtler abstractions. But actually, parts of pure math are always finding new and unexpected links through which they illuminate real-world situations. And conversely, all the sciences are continually spinning off questions that raise new mathematical problems and propel mathematical research in new directions.
So I'm thrilled to be able to talk to you about the world according to David Mumford. And I'd like to start by asking you to just say a few words about your groundbreaking work and most well known for in mathematics.
The core of my work in mathematics centered around the problem of what's called moduli, which is essentially making a map of the whole collection of a certain kind of mathematical object, namely a Riemann surface, or it's also called an algebraic curve. So you take the totality of these with a fixed topological type, and you consider each of those just like a map of the world has a point on the map for every point in the world. A map mathematically is another mathematical object which has a point on it for each isomorphism class of algebraic curves. You're classifying it, you're getting an overview of all the objects of a certain type. And so I would say this was a theme throughout my mathematical work. When I'd been an undergraduate, one of the interests I had was in studying what was known about the human brain and and people had just begun to make simple models of how the brain might be operating. There was a very seminal paper of McCullough and Pitts in which they had proposed this idea of a simplified model of a neuron and how you could assemble these together into more elaborate circuits which could accomplish some significant computational feats. So there was the beginning of a theory of how the brain might work. And it seemed to me in particular that vision as a subset of our cognitive skills was an area which was sufficiently well delineated that it didn't involve having to solve the problems of general AI and the entire thought processes of the brain. It was a rather specific computation. And it's also an important fact that birds are very good with vision, as are octopuses. It seemed as if it's been solved multiple times by animals, and so why can't we solve it? So that was what really inspired me to go into computer vision. There's human intelligence and artificial intelligence, and they don't necessarily have to follow the same path in every respect. So in particular, I think human intelligence and animal intelligence is very much animated, you might say, by feelings and by emotions. In the lowest animals, I mean, starting with simply the feeling of pain, but then the feeling of bonding with other creatures. And I mean, this has very, very deep roots in animals. And it's absolutely unclear whether or not artificial intelligence should encompass emotions and feelings. And if it is going to ever do it, it's a gigantic challenge which almost nobody has even begun to address. But if you look, as we were talking earlier this morning, at purely the cognitive skills, the ones which really take place in the cerebral cortex and not in the lower parts of the brain, then I suppose artificial intelligence, there's no reason why it shouldn't encompass all aspects of cognition. So you certainly want to merge actions and robotic skills for precise actions and and robotic planning for more extended sequences of actions. And then this has to be informed clearly by a feedback loop involving touching and seeing and hearing, so all the various senses that you can also incorporate. And in the end, in the middle of the whole process, we have the issue of reasoning and forming a mental image of a collection of circumstances, which is a coherent description of where we're at, what we're thinking of doing, who we're interacting with, what our immediate goals and our longer-term goals are. I mean, this is the essence of what higher cognition is all about, and it, of course it exists in a less developed form in essentially certainly all mammals, and to some extent birds and fishes. So given a static image of the world, you want to find the outlines, for instance, of you sitting there, and your face, the paper in your hands, the coffee cup. So all these things, you like to have an automatic algorithm to pick out the various objects in that still picture. So that was a point of beginning, and in doing that, we tried to introduce a mathematical model instead of doing simply ad hoc programming. We wanted an abstract mathematical model of how this might be done. But after playing with these ideas for a while, I met Stuart Gieman and the professor who had influenced him a great deal, Ulf Grenander. Suddenly realized that there was a link between what they were talking about and what I was learning about the cerebral cortex, and that you could unify many of the ideas and provide a really good grounding for the theory of how vision was carried out by introducing feedback in the cortex and relating that to the idea of a prior distribution in statistics. So in Bayesian statistics, you infer things about the real world by combining the data you have in front of you with a prior, which is your best guess for the distribution of the things you're trying to infer in the real world. And then in the particular instance that you're confronted with now, you have new data, and you combine the two to get your best guess, the so-called posterior, about what you're looking at. Well, he just came in there, and the first time I realized that I was dealing with something special was when he took an hour exam, and he left one question blank because the answers were so obvious. He said, "This is ridiculous," and but he answered everything else perfectly, and he clearly was always way ahead of me. So I realized that here was a guy that was really one of those wonderful students who comes out and you know that they're going to be the leader in whatever field that they choose to work in. It was inspiring. I mean, he pushed every idea that a fragment of an idea that we had so much further, and began to develop his own ideas about the whole big picture. I mean, he was always following what... I mean, you see, computer vision had been, in the past, a more or less field of engineers exclusively who had... So we're looking for ad hoc solutions to particular problems. And so starting with Marr and then Song Chun, the whole idea that you really should have an overarching theory as to what you're driving at. We wrote a number of joint papers in which we developed specifically finding the right prior from huge amounts of data was something that we started doing. And of course now the availability of not just huge but humongous amounts of data has been the key that has unlocked neural nets and the contemporary algorithms. But he really started it, and a lot of people scoffed at it at the time. They said, look, you're running this computer for 3 days in order to get an answer. What's the point of that? I mean, the engineers thought that's ridiculous. And paid zero attention to it. But it made all the difference, because she was understanding the underlying theory by doing experiments. Well, really, neural networks go back to the 40s. I mean, although they've now sort of hit the big time in a big way, the initial ideas go back to McCullough and Pitts and Marvin Minsky and the people, that group at MIT that were perceptrons, doing very simple networks of very simple units, and then thinking that, inspired by the brain, we should have several layers of them. So one set of units does initial processing, and then their output goes to another layer which does more processing. And so this idea of multiple layers came in. And then there was a PhD thesis. So neural nets really took off when this back propagation algorithm was introduced, which enabled people to improve the weights present in the network. So compared to other statistical algorithms for analyzing data, neural nets are characterized by having millions, literally millions of unknown numbers that have to be fixed in order to have a working neural net. So how do you figure out the values for these millions of numbers that it has to use in order to do anything serious? Well, you're going to have to learn from data. So this is the backpropagation algorithm, and this seems to be, without a doubt, the part of the secret of why neural nets work as well as they do, that it is very well matched with this learning algorithm, and somehow or other, which is not fully understood, it avoids what's called the bias variance dilemma, where if you have too many unknown constants in your algorithm, you overfit the idiosyncrasies of the specific data set and it doesn't generalize. If you have too few constants, you're smoothing the irregularities in the full complexity of the data, and you don't have enough to model the subtleties of the real world data. So that's called the bias variance dilemma, and somehow neural nets seem to miraculously avoid it. But it wasn't until humongous amounts of data and incredibly fast computers became available that all of a sudden they began to really work. And I think this came as a big surprise to many statisticians, but not Jan LeCun, who's been the guru behind this whole movement for many decades, and plugging the idea that neural nets were really going to solve a large part of the problems of AI. The other thing about neural nets, which is exciting and which is being extremely actively worked on, I view as bringing neural nets together with Ulf Grenander's view of what he called pattern theory. And what was always the key to Grenander's view was that if you're really going to analyze data, you also have to have a sufficiently accurate description of what you expect in that data that you can synthesize new examples. So you would like to be able to run the algorithm forwards and analyze new data, but you should be able to analyze it backwards and construct artificial data that actually resembles the data coming from the real world. So pattern analysis and pattern synthesis should be two sides of the same coin. And this has now become a very hot topic in neural nets, which I think is absolutely the right direction to go, so-called generative neural nets, which is definitely one of the areas that's actively So Song Chen and I have been talking for quite a few years about what we feel is one of the really big steps that needs to be taken. And we wrote a joint paper on the grammar of images. So our feeling is that grammar is not just something that applies to language. Grammar applies to all of thought. And what do we mean by grammar? What we mean is that there are certain higher level components. You have words in language. You have words of different types. You have verbs, nouns, adjectives, so on, and you have clauses, and you have sentences put together with paragraphs with themes. You have structure on many levels, and the important thing is that the analysis of what you're doing right now is created by a parse tree in which a kind of a graph is created which looks at the parts that go into this and gives the parts names and describes how the parts are related to each other. So the point of our paper was, first of all, to work this out in the case of images, to say what is the grammar of an image, how an image should be decomposed into parts, and what are the basic relations between those parts which have to be satisfied in order to make them fit together properly. So we have a whole scheme there, and it's also a scheme which I think we both believe can be generalized to other instances of thinking, and the kind of whole model that you're creating inside your head of the world that you're part of right now, and what you know about the past and the future, your plans. So all of this comes together really in a huge kind of parse tree. Mm-hmm. So one of the key phrases for this is reusable parts. You know, this idea actually goes back to arguably the greatest Arab scientist during the Dark Ages of Europe, and when Arab civilization was at its zenith. Ibn al-Haytham was his name, and he studied vision. And he realized that vision was actually a computation. It wasn't carried out by the eye. It was carried out by the brain. It was an amazing insight into a much really fairly contemporary view of what vision consists in. So, yeah, no, absolutely, and at this point that's the other problem with neural nets. They're by and large are black boxes which produce marvelous answers, but how they do it is completely mysterious. There's these millions of weights inside which somehow or other come up with good answers, but what do they mean? And perhaps it's the same in our brain, for that matter. In our brain, we have literally trillions of synapses, which connect particular neurons to other neurons, and it's impossible to sort of really interpret at any local level why the strength of that synapse is what it is. But somehow or other, hidden in this big network of units, whether they're artificial or they're neurons, at some point, these higher level ideas are being extracted and identified so that you can reuse them in new circumstances. So the brain really is somehow learning categories and higher level concepts. And I think that's the next step, is to get your neural nets to somehow be able to say, I've now discovered that there are cups in many images. Mm-hmm. That would be You'd say, hey, bingo, when that happens. You have to also say that the fundamental problem of how the brain works is actually completely unsolved. We can trace connections between different parts of the brain, and we know that activity in different parts of the brain is correlated to particular actions. I mean, it's an amazing fact that there's a particular operation which is performed on people with intractable epilepsy, in which a person has a part of their skull removed under local anesthetic, and then you can actually stimulate the human brain with an electrode, and the person who's wide awake will suddenly have a feeling, will see something or hear something, or want to move some muscle. We have no way to say, when the person pronounced a word, that certain activity came from a certain set of neurons that contained the right motions of your mouth and your tongue to say that word. So, this is I think neuroscience is in a field which is like all of biology was before DNA was discovered. It's in a pre-DNA state where no one. So, therefore, AI is in the same state. We don't know how difficult it's going to be to integrate neural nets with grammars. It may turn out to be a 5-year project. It may turn out to be a 50-year project. I think we really don't know how far we have to go. I visited his lab at UCLA, I don't know, I think at least 3 times, and had a sort of show and tell with his graduate students and had extended conversations. And he followed a path which is, to me, a completely logical and natural one. So from the early work in which 99% of our efforts were engaged in analyzing static images of the world, he moved on to movie clips and analyzing motion. So first you have more or less straightforward things like a bird flying or a person walking, and modeling this. And then from there he goes on to small scenarios in which people, mostly his graduate students, would walk into his lab, make a cup of tea, go over to their computer, work a little bit, stand up and pace around trying to figure out how to do something. In other words, he was now analyzing sequences of actions which are put together in which people had goals in it. And in doing this, it wasn't merely that he was engaging in more and more sophisticated portions of thought and AI, but it's also that he was building, while he was doing this, more sophisticated grammars which described the situation. So, and in particular was integrating his ideas with other pieces of research which involved constructing graphs of things. So you have, in time sequences, you have Markov processes, and then Judah Pearl was modeling things with these directed graphs in which certain higher level ideas explain what you're doing at a lower level.
Pearl was a big name when I was a student.
So he was the person who pointed out that in the popular mind, people often take correlation to imply causation, and what a tremendous mistake this is, that things can be correlated where neither is causing the other. But usually, when you have things that are correlated, you have a common factor, which is a partial cause for both of these at a deeper level. That is really the causative factor, and he developed basic ideas as to how you analyze causation in the real world. And I think and for that he was awarded the first Grenander Prize from the American Math Society. The thing which was really unique about Ulf Grenander is the breadth of his vision. I mean, many statisticians really tunnel into very precise questions and develop very, very sophisticated tests for a very particular kind of data. Ulf's idea was really that statistics really lay behind everything in the world. And in his work, he was always looking beyond what other people were doing. And way back in the early 80s, for instance, he began studying the statistical model using Markov random fields as opposed to Markov random models, which were two-dimensional and linked to this problem of segmenting images and finding the objects in images. And then around 1990, he and a set of collaborators, Yali Amit, Mike Miller, began to develop statistical models for the shapes of objects and modeling shapes. And this has become a major industry in medical imaging and interpreting medical images, which was a dream that Ulf had. And he wrote this letter to a group of us and said, "Fasten your seatbelts," it began. And he proposed this whole thing that we should build models of the entire human body with all the organs in it, and together with the statistical variations in normal, physically healthy bodies, and the more extreme variations in diseased bodies, and that this should underlie all the interpretation of medical data. I think this is really a fascinating mystery. As I grow older, I put a certain amount of thought, as I think most older people do, to the nature of life and what characterizes being alive and being consciously aware. And I would break consciousness down into three elements. Cognition, that which is what AI is really attempting to model. But you can imagine a person who, is, for instance, is dazed, or maybe they just woke up, or maybe they some event and they can't even think clearly. There's nothing conscious in their mind in the way of precise thought about anything, but they're aware that they're aware. So I don't think consciousness is the core. Is cognition. Cognition is something carried out, but in certain times you basically are aware of that you're alive, but you're not really thinking about anything. I mean, of course, the Buddhist monk meditating is the extreme, where you work extremely hard to wipe your entire brain free of any thoughts. And if thoughts come, you're supposed to just brush them aside and let them disappear. That's what they always tell you to do. A hard thing to do, in my experience. But, okay, so that's one layer of consciousness. The next layer of consciousness, which I think is deeper, are feelings, because everything from pain to love is something which you see clearly in lots of animals who have relatively small abilities to reason about anything, but appear to have feelings of this kind. Now, whether or not, I think in principle, one ought to be able to teach an AI to understand, at least in some cool calculating way, like Mr. Spock in Star Trek, was supposed to have no emotions, right? But maybe was startled when Captain Kirk exhibited an emotional reaction to something, but it didn't throw him. He understood that humans had this weakness; they had emotions. Yeah. So I can imagine an AI being eventually taught about emotions, although I think it's going to be a big battle itself, because emotions are so much more complex. The only people that really understand emotions are novelists. I mean, no scientist has any theory of emotions. But deeper than either of those, I feel, is really the core of consciousness, which is that you're aware of time. That, you see, in physics, especially since special relativity came in, you cannot model the universe as the whole universe as having a past, a present, and a future, because our present and the present of someone, on a planet and the star Arcturus or something, there's no way to correlate our notion of time with theirs. Time is completely a subjective thing for this particular point in space, in which, as I move through space-time, I integrate the indefinite metric of space-time, and I get my subjective consciousness of time. But the fact that for us there's this unique thing called the present is also almost by definition excluded from science, because science seeks a law which will apply to things in other times and other places, and is at least to a certain degree universal. So it kind of excludes the whole notion of the present. So anyway, in my blog I was very pleased to find that Einstein was on the same track and felt that this was something that science couldn't really encompass either. And I believe that to be the deepest level of what consciousness is the awareness of the present.
But Gracie and Thule may, in fact,
I fully believe that they experience the present in the same way that I do.
How would you see AI in terms of its ability to help humanity?
My biggest fear is that it's human nature to want to feel useful and to work, to carry out and to become really good at doing a job that is helping your family and your children, and then you die saying, I've done something good for the world. And I see AI as displacing so many people in the world, and they're being left with really no jobs to do. And that image of the world, I think, is terrifying. I had a big argument with Roland Fryer, the economist at Harvard, and I said, Roland said that the world has gone through so many transformations, and in each transformation, new jobs have always appeared, even though the old jobs disappeared. And he felt confident that there was nothing fundamental that was happening now that was going to change that. And I hope he's right, but I'm not confident. I'm terrified that successful AI may seriously permanently take away work from a large percentage of working age humans, especially if with medical advances our working years are extended by an order of magnitude. Maynard Keynes said that way back in the 20s. He predicted that it was just around the corner and that we would all have 20-hour work weeks. And if it weren't for the concentration of wealth that we have in the world today, there's no reason at all why everyone have 20-hour work weeks and all have decent productive jobs in which we produce just as much.